and more. So in the next few 20-25 minutes, I'll just share you what we are currently doing the last 10 years. So as just to give us some introduction, currently the CIMMYT-Africa maize breeding program, we have 5 product profiles in total. These 5 product profiles in Eastern and Southern Africa, which is serving around 40 million hectares. The three is Eastern Africa product profile 1 to 3, and then we have 2 in Southern Africa. And the target country, this is the main or target country, and there is also some spillover countries, and you can see the area served by each product profile. Just to give you also some background, so this is our stage gate process in CIMMYT maize breeding program. We have a line development team, which is responsible just to make crosses, making stage 1 and stage 2. And then we have a product development team, which focus only stage 3, product identification, and stage 4. And we have a seed system team, which is going to the on-farm trial. And then we have products announcement, licensing, a national performance trial for release and commercialization. And then the nurse partners in all Eastern and Southern Africa, they are also involved with starting from stage 3 to variety release and commercialization. Initially, I think the last 2 years, we have been now, before 2021, we are recycling line either from stage 3 and stage 4. That is probably it will take around 4 or 5 years, one breeding cycle. But starting 2021, so we are now moving a recycling line from stage 2. So as soon as we evaluate the material after stage 2, we select material and then use in the breeding process. So currently we are using both a DH and the pedigree method. We have a DH facility in CIMMYT Nairobi, and then some of the activity also pedigree method when we are just using some of backcross and integration material. So in terms of the criteria for product advancement, we have, as I said, stage 1 and stage 2, the responsibility is for the line development team. So we are just, so all the material in stage 1, we are genotyping with a medium density marker. And then we have also some functional marker for MSV and MLN. So as soon as we receive a DH line, when we plant for seed increase purpose, and we genotype for MSV and MLN marker, and then we discard those susceptible. And the second stage is all those materials which pass that MSV and MLN, they will enter to stage 1, and then at that time we'll genotype with a medium density marker. And then stage 2 to stage 3 is also the same line development breeder, when we are try to figure out the GC of the line. And stage 3 and stage 4 is a product development team, and we have a product advancement team every year, including a nurse partner. We sit down and then advance those hybrid which meets the criteria for each product profile. So this is just to give you, this is Eastern and Southern Africa, and this is a market segment which is served by these 5 product profiles, starting from Ethiopia to down to South Africa, as the colors are for different product profile. And this is a trait we are just following, and then this is a product target for advancement, and we identified some benchmark hybrid which want to replace, or which can just, this is a competitive hybrid in each market segment. So this is some of the activity. And then in terms of maize breeding in Eastern and Southern Africa, we have several stresses. We have a drought, which is one major stress in Eastern and Southern Africa. we have this maize lethal necrosis, Terticum leaf blight, and GLS. At the same time, also we want to develop hybrid, which is performant good when there is enough rainfall. So we try to sample the target population of environment, and then based on that, we'll just advance those hybrid which meet the criteria. So when we just come to a GS, in CIMMYT breeding program, genomic selection is currently applied in two ways. One is rapid cycle genomic selection. This one,
No.
Sorry for that, Joseph. Let me just mute the people. Can you unmute yourself also, Joseph?
yes, thank you.
Yeah, sorry.
Yeah, so we started this rapid cycle genomic selection 6-7 years ago when we have this biparental population. And then recently, 5 years ago, we have also started to predict the performance of unphenotyped genotype at early stage of testing. So I will give you some of the results from rapid generation using genomic selection. 6-7 years ago, we had big two projects. One is drought tolerant maize for Africa, and another one is water efficient maize for Africa. So during that time, the initial idea is marker assisted recurrent selection when we start as initial stage, and within a year or two, we instead of marker assisted recurrent selection, just we used all the markers just to predict the genetic estimate breeding value for individual plants. So during that time, we advanced more than 34 biparental population, each with approximately 184 families per population. And we evaluated them under 2 to 4 managed water stress and 3 to 4 well water environment. And we genotype at that time with a high density marker, at the same time with a low density marker. And then we did some genetic gain study to see the difference between. So this is a workflow. I will not go in detail. When we start 7-8 years ago, so we select material within heterotic group, line A cross with line B. We generate F1 and F2, or we have to do some polymorphism screening for the parent, and then also quality control. And then F2 derived F3 line, that is the time when we make test cross with opposite tester, and we evaluate those test crosses across location, and those are used as a training set. And then that one, we call it a cycle 0. And then cycle 1 is use all the marker, and then recombine before flowering using a test cross of a particular population. And then we did the same this for cycle 2 and cycle 3. And then at the same time, just want to make sure not to follow the whole population. A few population, we advanced some material using pedigree. And then finally, we did some genetic gain study. And from that cycle 3, we submitted for DH induction. So we developed several DH line. I'll show you some of them are currently the parents of unlocated hybrid. This is the training set. So the training set, all those population has to test cross, has to evaluate it under drought, under disease, and then under optimum condition. And we will use those phenotypic data to advance 2.5 recombination per year. So this is the first, the one we did around in 2015. So out of that, we just took 8 population, and you can see now the difference between cycle 0, the black one, cycle 1, cycle 2, cycle 3. So it is not consistent for all the population. It just depends on the population type, but on average, the genetic gain per year is around 70 kilogram per hectare per year. So this is under drought. So if you compare this one with conventional pedigree breeding, which is done by Masuka in 2017 from Southern Africa regional maize breeding program, and the drought is 32 kilogram per hectare per year. So this 70 kilogram per hectare per year is almost double. So this is under drought. And then because our focus is product development, and then we developed those DH line from cycles 3 and then made several hybrid. You can see this is also, and the one which is the blue is a top hybrid which develops through rapid cycle recombination, and then the red one is the parent, and the green one is a commercial check. So you can see grain over the commercial check ranges from 8.7 to 20%, and then over the parent from 9 to 91%. And the under drought, this is under optimum. Under drought, the gain is even very high. You can see 17 to 53% compared to the parent, and 47 to 98% compared to the commercial check. So that is just to show you line developed through rapid cycle genomic selection and used in hybrid breeding program, and they are consistently higher than the commercial check and the parent. And then this is a one, currently this is a 5 line, which is developed from marker assist selection from cycle 3. And then this is a number of hybrid currently allocated to different partners. So some of the lines are being used in the commercial hybrid. And this is just to show you some of the line developed through rapid cycle genomic selection. And this is a ear, and this is a plant. And then because the DH line, so we are currently also using those one in different hybrid combination. For example, this is a picture I took in 2021 from Kiboko. In Kiboko here in Kenya, we have a managed drought screening site, and we plant the material during rain-free period. And then we stop irrigation 2 weeks before flowering, just to see the difference between susceptible and drought tolerant. You can see 2 rows of maize, which is still green, and you can harvest reasonable yield compared to those susceptible material. So that is the one we did previously, and one of the challenge from that work is it is the phenotypic cost, because in each population you have to make a training set for particular population, and that is very costly. So if I say, for example, 34 biparental population, and if you generate around 184 per population, you have to evaluate more than 6,000 hybrid across locations. So that is one of the challenge. And then starting 4 years ago, so what we did is, because we are generating a lot of DH line per product profile, and we can't phenotype all of them. So what we did is, for example, in this year, in 2018, we have more than 2,500 DH line, but we could only phenotype around 855 line, and we genotype all the material. And so we use this 855 as a training set. So you can see here, on the right, the relationship between the training and the testing set. So, and then here is a predicted and observed value under optimum and drought. So using this 855, we predict the remaining lines, and then we select those for next stage testing. And at the same time, also we used, instead of only marker, for example, this is in 2018. This is the correlation between the observed and predicted only using marker. But if you include also the pedigree, it's not much different. This is the correlation is 0.85, and this one is 0.89. And under drought, 0.72 and 0.77. So you can slightly increase the prediction accuracy. This is a cross-validation. So in CIMMYT, we have two heterotic pool. One, we call it heterotic pool A, and another one is B. So what we did is, if you use a tester one and to predict, so this is a training set in tester one, and this is in tester two, you can see, and if you use across tester using 853, the prediction accuracy is slightly higher compared to using tester one and tester two. But I think the only thing here is probably a low accuracy in tester one might be related to the size of the training set. But in tester two, you can see there is no much different adding additional 1 from tester one. So both across tester and within tester, the prediction accuracy is similar. So this is the one we did 2 years ago. And then this is, sorry, what, okay. Yeah, so this is just to give you how we did it. For example, this is one population. This is CML 536 by La Posta Sikea. This is one of the drought tolerant and low nitrogen tolerant donor parent. So we had 166 DH line, and we said, okay, let's just only phenotype half of them and predict the remaining one. And then lines selected based on the phenotype. Once we do the prediction, we selected 21 line compared to the commercial check. And then we also selected lines based on genetic estimate breeding value around 19 lines. And then, so this is how we receive the data from our quantitative genetics and biometric unit. So this is a selected line, the one which has phenotypic data. This is observed the optimum value, and then this is just predicted based on the marker. And the one which is a green one, this is under a managed drought. This is the observed phenotype and then predicted. If you see the one which I highlighted in blue, those material, those DH line, we haven't phenotyped. We always just predicted. So we selected this some of around 19 line based on only GEP and the performance under drought. And so what we did is just to compare what is the performance in stage 2 trial. So, so this is, we selected 348. This is a total number of DH line which went from stage 1 to stage 2. This is across all the population. The previous slide is only for just one population to show you what our protocol. And then this is the number of testers, or this is the total number of hybrids. So out of 1,000 hybrid, 526 is coming from based on stage 1 phenotypic selection, and another 566 only based on genetic estimate breeding value. So we evaluate those stage 2 material across location and drought. So if you see here, the one which is a circle, there is 93 hybrid. This is just the mean for all the hybrid. This one around 1042. And so we selected the best hybrid around 156, regardless they came either through phenotype or genotype. We just select the top 157 hybrid. So when we just see out of this 157 hybrid, 93 came through phenotypic selection, and the remaining 64 came from genetic estimate breeding value. And when we compare them, means there is no much difference the mean performance, those advances through phenotypic selection or genetic estimate breeding value. And the same is true here for drought. So the one thing is under optimum, we have 93 hybrid, which came through phenotypic selection, but under drought, there are 91 hybrid coming from GEP. So that might be, we have more location under optimum compared to drought. So it suggests that under drought, we have only one location, and the marker is better compared to the optimum. But under optimum, we have 3 optimum location, and more hybrid are coming through phenotypic selection compared to genetic estimate breeding value. So although the performance are the same, the difference is in terms of the cost the cost benefit ratio. So you can do almost 70% of the cost using, or in other words, there is a reduction of 30% of the cost by using genetic estimate breeding value, because at that time it costs us only $10 to genotype, but you have to, it costs you around $40–50 to phenotype at 4 locations and making a test across. So that is the difference between in terms of cost saving. Sorry. So this is just simply to show you, yeah, this is the top, for example, this is a commercial check, the one highlighted in yellow. And then this is the hybrid. So we selected the top hybrid. This is advancement. Some are coming from phenotype, some are from genetic estimate breeding value. This is a yield stage 2, and this is a percentage increase, and the same as for drought and some of the agronomic traits like moisture, disease, and ear rot. And then because we had also data from a couple of stage 1, we have data for 4 years. And here we just try to see, can you use the historical data to predict the next year new stage 1? So we used the 3-year data in 2017 up to 2019. We have 3,000 lines, which has phenotype and genotype. And genotype with around 5,000 marker. At that time, we were using RAM-seq. And then we did a different scenario. What do we just say? Okay, if we use a 2017 data, can you predict the 2018 or 2019 data? That is one of the questions we want. Another one is if you use 2017 and 2018 data, can you predict the 2019 data? That is one. Another, we just said, okay, for example, this is 2017 data. We have 923, which has phenotype and genotype. And then we want to predict the 2018, this 1,423. So the first one is just simply using 1-year data and predicting the second. And the second scenario, we said, okay, instead, can we just move 10% of the data from 2018 and include it as a training set in 2017, and can you predict the remaining one? So, and then this is as a distribution of those 3-year data, 2017 with the red, 2018 the blue, and 2019 is a black. So this is a number of DH line, phenotype and genotype. So here is the result. So if you want to use only 2017 data and then predict 2018, you can see the prediction accuracy for grain yield. This is for grain yield. The prediction accuracy is relatively low. But if you convert 10% from 2018 and include it into 2017, the prediction accuracy is significantly increased. And then if you also convert 30%, 50%, 70, and 90. So this is just consistent across all the years, 2017 and 2019. So using 1-year data, predicting the second year, the prediction accuracy is relatively low. But if you convert only 10%, from the prediction set to training set, the prediction accuracy significantly increases.
Can I ask one question for clarification?
Yes.
These different years, are they the same set of lines, or is it a different cohort of lines?
It is a different cohort.
Right.
Yeah.
So
Yeah.
I think you're missing a check here, and that would be training on the 10% only.
Yes. So 2017. So I have a set of say 1,000 DH line, which went to stage 1. In 2018, I have another new set of 1,000 DH line. Because we have the data, if we just convert 10% of the 2018 and put it together with 2017, and so that connectivity, or 10% connectivity, you can increase in both years. You see, this is 2017, 2018, 2017, 19. So that is probably that connectivity issue. Between 10 to 30%, but if you convert to 50%, there is no much difference. So even converting 10% is very good, but from 30 to 50, 70, and 90, there is no much difference in all cases. So that is the result we got.
My guess is all your accuracy is coming from that 10%, but anyway.
Yes. I think, yeah. And then what we did also, okay, can we use 2017 and 2018 data together and predict the third year data? The same, so that's a slightly increase. If you use 2-year data predicting the third year data, the prediction accuracy and the well water and also stress is 0.32, you can see here. But the same, if you convert now 10% and put it in the training set, you can increase the prediction accuracy. So that is the one we did. And so that is some of the activity, just to show you that. So what we did is this one is we implemented this the last 10 years. And then we did some genetic estimate for 10 years. And then, so this is just the one product profile. And you can see under optimum as a genetic gain. So this is using stage 4 data for the last 10 years from 2011 to 2020. This is the number of trials. And you can see the genetic gain is around 1.61 under optimum, and then 2.4 under drought. So this is just tells us at least we are on the right track. So the next few slides is we are also doing a continuous improvement plan. So this is the work done by EIB in collaboration with EIB, Eduardo and Chris, to see, because normally we are just recycling at stage 3. So what is the benefit if you recycle at stage 1 and stage 2? So this shows that there is around 17 to 90% of genetic gain compared to stage 3. So this is also one of the reasons we shifted our recycling to stage 2. And we are also doing some sparse phenotyping, just to say to sample the more target population of environment, and then using only and then so this this shows that if you use a complete phenotyping, this is a solid line, a complete phenotyping, and then you use the sparse phenotyping at a different level, and if you reduce around 20% of the phenotyping or 30%, as accuracy is you can almost 90% of the time you can select the top hybrid both under complete phenotyping and the sparse phenotyping. So this is at least good, which allows us to sample more environment. Instead of planting all the hybrid in all location, we can do some kind of sparse phenotyping and then get the prediction using marker for each line. So another activity we are currently doing with AIB Module 2 team is to use a selection index, especially if you want to go to recycling at stage 1 or rapid cycle genomic selection. So this is a desired software, and which gives you a total genetic merit for a particular line. So in this case, we have an example of 600 entries. So for example, now we can just select the top line, which has a very good total merit. And this is just to show that those we selected by using this software compared to non-selected material. So if you see here, the one which is grain yield under drought, grain yield under nitrogen, and grain yield under optimum is a desired level, whereas others disease resistance we are reducing. So this is one which is useful, especially we want to move to now rapid cycle genomic selection. In that case, you will use a selection index to advance those material. Another activity also we are saying is, okay, if you want to move to recycling at stage 1, you have to a little bit reshuffle the testing strategy. So stage 1 should be at least a reasonable environment. So this is a retrospective analysis. For example, this is one of the regional trials. We evaluated around 35 locations. And then this is in 2016 and 2017. So I just sent this data to Eduardo. So he's seeing, for example, there's a red dot line. This is the number of locations for stage 1, stage 3, stage 2, stage 3, and stage 4. So stage 1 is currently we are using around 4 locations. So this retrospective analysis shows that if you evaluate your stage 1, for example, at 7 locations, the breeding value, the correlation of the accuracy, 7 locations compared to 35 locations is almost 0.8. So currently it is around, if you use only 4 locations, the accuracy is also 0.7. So this is consistent for all the 3 years. So that means from the current 3 locations, if you go to up to 6, 7 locations, you can almost 80–90% you have accurate in selecting individual for recycling instead of going waiting stage 4 or stage 3, which is around 15 locations. And this is another activity. So say, okay, which location is more useful in terms of heritability and genetic variation if you want to select 5 or 7 locations for stage 1. So this is the same analysis using data from the previous year, how to identify the best location. The last activity is also we are working with Kwan, CIMMYT biometric unit. For example, here I have these 302 lines. This is a state 1, state 2, state. All of them are crossed with 3 testers. So we have close to 700 or 900 hybrids. So because we have a genotypic data for each line, so what Kwan did is, okay, if only the 48 lines is crossed with 3 testers and the remaining 85 line with 1 tester, another with the second tester, and the third tester, and then we want to predict the performance of those. For example, the first 85, what is the prediction accuracy in tester 2 and tester 3? And if you see the result, for example, set 2, that means this 85 line, and we want to predict the performance in tester 2 and tester 3, the accuracy is very high. And the same for the next line, and the same for the next line. So this also gives us some hope. So in stage 1, we can also increase a tester and keeping the total plot size the same by using sparse test crossing. Okay, so this is my slide, the last slide. So what we learned so far. So this is not work for a particular group. It should be a good, proper planning and coordination among the conventional breeder, molecular breeder, biometrician, and quantitative genetics, especially if you want to recycle before flowering. So the logistics should be as soon as you plant, leaf sampling, sending and then getting the data before flowering. And then this also the service provider, it should be very reliable. Otherwise, if you lose the flowering date, so the whole activity miss the point. So currently, we have a service provider in Australia, the DART. So actually, we sent the material 2 weeks ago. So now we are waiting to receive the marker data. And another most important is point 3, a database which can link genotype and phenotype. Sometimes it is not easy currently. There is a lot of manual process. But once EBS is currently in the pipeline, that will reduce this issue of linking phenotype with the genotypic data. I think the last point is a common genotype platform. I think now we are moving to the DART. I think that is my final slide. Thank you very much for your attention. Thanks.
Thanks, Joseph. That was terrific. That was a lot of good content. Probably too much of good content. I see many questions at this point, Joseph, and we only have 15 minutes. So I'll try to do my best to pass some of these questions to you, and the ones that we cannot cover, I think that's fine. We can go over them later on. I think a recurring question in the chat goes about the use of the sparse designs, Joseph, in terms of genotypes or in terms of environments. I think if I can summarize some of the questions, seems to be like you can use the sparse designs to keep the sampling of the genotypes and the same sampling of the number of environments, but at a reduced cost, or use the sparse designs to cover more the TPE or cover more genotypes. And the questions basically go in what is the direction of the CIMMYT-Maize program, trying to sample more at the same cost or trying to reduce the cost and cover the same. Can you comment on that, Joseph?
Yeah, thank you, Eduardo. I think for what we are thinking is the resource is limited. So for example, I think the intention is to sample more environment. So we have a fixed cost, a fixed plot. So instead of replicating in all location, what we are trying to do is just to sample more environment so that increase that accuracy. So the intention is not reducing the cost. I think it's just we want to sample more environment. So that is the current thinking for GMEP.
Thanks, Joseph. Then there was another question from Godfrey on the stage 1 testing. The question, I don't know if I understand it properly, it says, are you using this one tester per heterotic group or across heterotic group in stage 1? I assume, yeah. Do you want to say something, Joseph? I don't know.
Yeah, so what we are using is one tester. So if our line is heterotic group A, our tester is B. And then when our line is B, the tester is A. So in stage 1, we are using one tester from the opposite heterotic group.
Right. I don't know if someone wants to raise their hand or just jump in. Gary, do you want to make a comment? I see your hand raised.
Yeah, thanks. Very nice summary of a long history of work on this issue. Yoseph, two things come out very clearly, both from this work and from the literature, work other people have done, which we really need to make sure we're completely up to speed on. One is we need to move to selecting parents out of stage 1. We need to get that next year out of the breeding cycle. So this should be you know, there's really not much reason not to start now. The main reason would be the single tester. So there's very good data to show that, you know, once you've got the genomic relationship matrix, linking together full SIBs at stage 1, you don't need to have every entry on every tester. You can predict, make a very nice GCA prediction from the sparse designs that you were discussing. This doesn't need, a, you know, it needs a little refining, but not much at this point. We should be, what are the plans for implementing these two important changes soon? These are the really where we can expect to see fairly major increases in the rate of genetic gain per year, seems to me.
Yeah, thanks, Gary. I think both comments are valid. I think the first one is recycling at stage 1. We have a plan. Actually, we started this year. Currently, we are planting F2 drive at F3, and then we send the material for genotyping. So we will implement that. So we were discussing internally just to move a little bit of resource for stage 1 testing to increase that accuracy. And then the second point you mentioned is, yes, we are in agreement. Instead of using that one tester in all stage 1, we can use like sparse test crossing or incomplete, so that we can predict the GCA for that line. So both your comment is valid. I think we start implementing this year, and then it will move to the other product profile next year. Thank you.
Great, thanks.
Yep, thanks, Joseph. If I can just, make another question, since we don't have other hand raised. You were showing, this nice picture with the little box plots, and I don't know if you can also share it again on the screen while I make the question. I think this is a really nice picture that I keep emphasizing when we talk to other people from your paper, because it shows exactly the type of accuracy that people will find when they move to this aggressive way of GS. The very first box plot where the accuracy seems between, well, yeah, that one as well, but the next picture I think summarizes the same information more or less. This accuracy between 0.1 and 0.3, or maybe 0.37, something like that. That's normally the type of accuracy in the best case scenario that people will find when they move to the aggressive GS, because you're trying to predict something that you have never observed. That is like this year trying to predict a future year. But we want to say that, this accuracy is actually not bad, because if you think about it, it's low, but it would allow you to actually move really, really fast, right? This is the type of accuracy that you would find if you try to predict, let's say, the F2s. So if you are in this range between, 0.1 and 0.3, it's low, but you are moving also really, really fast. And as Gary actually pointed out, the rest of the box plots, the accuracy goes immediately super high, because you're pretty much, predicting material that you have observed, but you wouldn't see that type of accuracy in the aggressive GS. You would see that type of accuracy in your sparse testing designs, in the ones that you showed, right? Anyways, this is, so the question, Joseph, is how are the plans, for this aggressive GS, the very quick recycling, even, more aggressive than stage 1, but even going to the very early generations? Can you share with the people, your plans about this?
Yes, Eduardo, I think that one is, yeah, so for the time being, so for example, just one product profile. So for the time being, we said yes. So we are not completely moving to selecting parents based on, we can, depending on the proportion, okay, we can just select those from rapid cycle recombination, and then a few elite line from after stage 2 or probably after stage 2 testing. So what we did, I haven't shown this in this picture, is so for example, currently we have the two population, not two population, two. I think one is in 21 and another one is 20 population. So we moved to F1, F2, and then we want to use the training set from last year. So when we plot this, the F1, there are a very good relationship with the previous year. And so we are using that one as a training set to recombine. So this year we'll recombine at least 2 seasons per year. In Kiboko, we have a irrigation facility. So the idea is to move on that direction, but we have to also do a little bit of this resource allocation so that at least the stage 1 data, we have a good training set to predict those material which goes to the next recycling. So yes, we are in that direction. Probably next year we'll have some result on that.
Yep, thanks, Joseph. There is 2 hands raised. Our colleague from ICARDA, Sanchez Garcia, can you jump in?
Sure. Thanks, Joseph. Really nice presentation. Lots of results there. My question is, if I understood correctly, you're using right now 5,000 markers for your GS predictions. Have you tried reducing the number of markers? I'm just wondering because if we, for example, we need to match this marker density as per the genome size with other crops like barley, even that is also a diploid crop, that would mean a lot of markers for us. So I'm just wondering if you think we can get the similar results with lower number. Thanks.
Yeah, thank you very much, Sanchez. I think those 5,000 is it was in our collaboration with Cornell University. So the cost is around $10. At that time, we had a good collaboration with CIMMYT, and then so who gets those 5,000 markers. But recently, what we did is we moved to DART, which gives us around 3,000 markers. So we did some comparison to see is there any effect marker density. The prediction accuracy using RAMSIC 5,000 marker and then 3,000 from DART, there is no any difference in terms of prediction accuracy. So we are moving to now 3,000 DART marker for rapid cycle recombination.
And if I can add something there, just to add to Joseph's comment, yeah, I think it has been proven, in practice and also in simulations that, really you don't need that many markers. Really the number of markers, let's say that you can start in 1,000, 2,000, 3,000, 4,000, everything will behave the same for GS. The only difference will be that as the time passes, the training model, would require more and more markers. But the 3,000, 2,000 or 5,000 markers is more than enough to run a good GS pipeline for the next 30 or 40 years. Then you would need to basically have more markers. And also, of course, it depends on the population size and things like that. But in general, as Joseph mentioned, the 3,000 is still safe. Actually, 2,000 is very likely to be safe, and 1,000 very likely to be like 90% of that, the same accuracy. But as time passes, that changes. You might need more because you start to break some recombinations, and then you are not capturing certain linkage disequilibriums. But like I said, with those 3,000 that Joseph mentioned, is safe for the next decades. Joseph, there's still one more question, probably the last one from Pancho. Pancho, do you want to jump in?
Yes, yeah. Many thanks, Joseph. I wanted to ask you, you show a slide where we use pedigree as well as markers. Is only one. Do you think that the adding the additive genetic metrics to the genomic relationship metric will improve the prediction or will remain the same in maize, in your breeding program, in your rapid cycling?
Yeah, Pancho, I think that question is, the answer is from you. I think you know exactly.
Yeah, no, but
that was a tricky question.
is there any hope that we are going to have more information to be able to add the A metrics to the predictions and perhaps improve it or leave it as it is, which are very good actually, the prediction structures.
Yeah, so I think it's currently what happened is, I think, Pancho, you know it now, in headquarters, they are moving data from the Maize Finder to EBS. So it will take some time to get the COP for those material, but definitely I think if we include that one, it will add some prediction accuracy. For the time being, the one I showed, that one is there is a slight increase, but currently the system, when they move that one to EBS, that functionality is still, it will take some time to work. But this is just my own thinking. I think it will increase a little bit more information if we can get the accurate COP for all those material.
Yeah, I think this is something indeed to be discussed and checked, right? Because I want to emphasize that, you know, when people was using the pedigree, of course, there was no marker information that moment. It gives a high increase in accuracy. Then, you know, when the markers came, basically we're able to capture not only the family relationships like the pedigree, but also the Mendelian sampling. But, you know, some of the literature, when they have suggested the combination of both matrices, it's not because they are suggesting that this, the combination is necessarily, you know, better, but actually has been proposed to cover for gaps, right? Because some individuals sometimes are not genotyped. And this is where really the single step approaches, where they bring the pedigree matrix, help, because it's like covering for gaps. But it's not to say that actually, you know, there is this range, right, from the pedigree to the markers, and putting both, in some cases, is not necessarily that it's going to increase it. It might decrease it, actually. The pedigree, in that case, is to help to cover the gaps. But I might be missing something, but actually combining both, when you have complete genomic information, I would actually think that might not necessarily, you know, give you an advantage. Because the markers should be also giving you both type of relationships, the family one and the Mendelian sampling. But yeah, that's something interesting to be checked. There is, we came to the end of the meeting. So thanks a lot for everyone on your questions, on your comments, and Joseph, especially to you for, you know, accepting to give this presentation and sharing so many results, you know, with all of us. You know, if you still have a question or comment that you feel that it was not addressed, feel free to, you know, drop a message. I'm sure that Joseph will be happy to reply at least a couple of emails. Just please don't overwhelm him and just contact us if you want something else that we can support you with. I'll make the recording, you know, available in the next hours if someone, you know, wants to look at it again. Other than that, you know, have a great day. Thanks for joining. Thanks, Joseph.
Thank you.
Presentation. Thanks.
Thank you.
Take care, everyone.
Thank you. Gracias. Bye.
Bye.